All right, here's how the marking is going to go, okay, for the first three. Okay, you're going to get 1 mark for correctly identifying the reaction type. You're going to get 1 mark for having it written out in words with no mistakes. Okay, and you will get a 3rd mark for having it balanced correctly. All right, 3 marks for each one. Okay, so for the first one here, I've got an element reacting with an element to form a compound, which is what kind of reaction? It's a synthesis reaction. Okay, so 1 mark for synthesis. Okay, now next thing, I need to write it out in words. Be is beryllium. Okay, and it's reacting with oxygen. And that is making beryllium oxide. Okay, they have to have all of it right in order to get that mark. Okay, now you kind of see where it's so important to be able to write names correctly, because if you mix one of them up, okay, why did I what? Oh, okay. My answer to that is usually I did that because it's right. Yeah, okay. Now we got to balance the reaction. The only thing right now that's out of balance is oxygen, so we have to go with that, even though usually we do it last. There's 2 of them on this side, so a 2 needs to go here, which gives me 2 berylliums, so a 2 needs to go there. So we're looking at 2, 1, 2. Okay, 1 mark if they got that. Okay, next one. I've got an ionic compound reacting with an element, producing a different ionic compound and a different element. That is a single replacement reaction, 1 mark for that. Okay, next. Got to write it out in words. This stuff is calcium carbonate. It's reacting with lithium. That is producing lithium carbonate and calcium. Whoa, got dyslexic there. Calcium. Okay. Now, we got to balance this thing. Right now, it looks to me like the only thing out of balance is lithium. Okay, there's 1 calcium here, there's 1 over there, there's 1 carbonate, there's 1 carbonate, there's 1 lithium, there's 2 lithium. So, simply putting a 2 here should fix it all. Okay, so we're looking at 1, 2, 1, 1 for their 3rd mark there. Hey, we're on a roll. Good. Number 3. Ionic compound reacts with ionic compound, producing 2 new ionic compounds. That is double replacements. 1 mark for that. Okay, written out in words. This one needs, it needs a Roman numeral, right? Okay, this is iron Roman numeral 2 oxide. And it is reacting with sodium bromide. Okay, and that will produce iron 2 bromide. Okay, and sodium oxide. Okay, it has to look like mine, guys. There cannot be any mistakes on any of the names to get that naming mark. Okay, guys, you can talk to your partner about what you got after. Okay, we got to balance this now. Looks to me like sodium's got a big number beside it, so does bromine, so we'll start with those 2. There's 2 on this side, 2 on this side, so I think a 2 here will pretty much take care of everything. Okay, 1, 2, 1, 1. Okay, questions on the first 3? Okay, for number 4, we got to write it out in formula form. Okay, then we'll identify the reaction type. Copper 2 nitride. So we got Cu and nitride. This is -3, so the 3 will come down here. This is 2, so the 2 will go here. So we got Cu3. That's a terrible 3. Cu3. Jeez. Cu3N2. All right, that is that is breaking down into its constituent elements. So we're looking at nitrogen gas. Here's the trick. It's highlighted on your periodic table. When it's by itself, it's a pair. and copper. Oh, come on, I gave you a full color spread there. Okay, come on. Okay, so what reaction type is this? Simple decomposition. Okay, so if they got decomp, simple decomp, give them a mark for decomp. Okay, this is what they need to have for the mark for the reaction. And unfortunately, guys, here's where missing this will cost you. You can't balance it correctly if you don't have a 2 here. Okay, so we need to go back over here. There's 3 copper, so you need a 3 there. Okay, it's 1, 1, 3. Okay, let's try number 5. I think that one will go a little better for us. Okay, so because I couldn't remember the prefix for 16, I just gave you the formula for that so you could just write it. Okay, C7H16, okay, is reacting with oxygen gas to produce carbon dioxide and water. No, you got one for the name, one for the balancing, one for the reaction. Okay, if they have that, they get a mark. That's what that should look like. It doesn't matter, guys, if they have H2O first and then CO2, that's fine. Apparently the wrong answer. Okay, now, special rules for balancing combustion reactions. Balance alphabetically and the rule of 2. Do I need to apply the rule of 2? No, 7 is an odd number. All right, so we'll start here. I need a 7 there. I need 16 hydrogens over here, so 8 times 2 will give me 16. 7 times 2 oxygens is 14, plus 8 more is 22. 1, 11, 7, 8 for the balancing numbers. Okay? 1 mark for the reaction, 1 mark for balancing, 1 mark for, what kind of reaction is it? Combustion, 1 mark for that. Okay, and number 6. Okay, tricky formula stuff here because we got a polyatomic ion. Potassium permanganate. Okay, KMnO4. Okay, that's potassium permanganate. Okay, I told you the story about the little purple crystals turning your fingers brown, right? Yes. Okay. Reacts with magnesium hydroxide, which is that stuff. That needs to be swapped and dropped to a 2 because magnesium is a 2+ charge. Okay, and that's going to form potassium hydroxide, KOH, -1 + 1, so that one's good. And magnesium permanganate, Mg, brackets brackets MnO4. Two. It is wrong if you miss the brackets, yes. Okay, so give them a mark if they have the reaction written that way. Then, next mark, what kind of reaction is that? It's a double replacement reaction. They're both ionic compounds, so give them a mark for double replacement. Now, we got to balance. Okay, I've got 1 potassium over here, 1 potassium over there, so far so good. 1 permanganate, 2 permanganate. All right, so I got to go back over here and make a 2, so I've got 2 permanganates on both sides. That gives me 2 potassium. So I've got to go over here and put a 2 there in front of potassium. That gives me 2 hydroxides, and there are 2 over here, so that's good. Okay, and there's 1 magnesium on both sides, so it's 2, 1, 2, 1. Okay, before you hand anything back, okay, let's look at number 7. You didn't have to do number 7, okay, but let's look at how we would do number 7, okay, because this is what we're going to be moving on to next week. Okay, we have only one reaction type that starts with 2 ionic compounds. What is it? Double replacement. Okay, in a double replacement reaction, who switches with who? Calcium and iron will switch. We just swap the metals in a double replacement reaction to make our new pairs. So that means calcium is going to end up with bromide. Okay, and iron is going to end up with calcium. All right, now we got to swap and drop these. Okay, iron was a 3 over here, so it's going to be a plus 3 over there. Okay, so we'll have FeCl3. Okay, and this is a minus 1 and this is a plus 2, so when we swap and drop, we have that. Okay, we now have our 2 new compounds over there. All right, was that all that hard? All we had to do was switch the metals, right? That's how you predict. You just look at what kind of reaction is it, what happens in that reaction, and you make the products. All right. Now, we got to balance it, obviously. Okay, so when we do that, we should have 3, 2, 3, 2. Okay, that'll work out. That's what, we're going to be working on that next week. Don't worry if you didn't get it today. But that's how you do the prediction. Okay, they need a mark out of 18. Okay, so give them a mark out of 18, put it at the top of the sheet, and then come and put them in the box. When you have handed in your quiz, grab a Chromebook. And when you get it, open up your Properties of Compounds lab, because we're going to go over that. Okay, so first off, hands up, how many people watch the podcasts while doing their lab report? Okay, next time I want to see all the hands up. Okay, because how many hints do I give? Lots, okay? And I don't expect that you remember them all. I expect you should write them down, but I realize reality is not that way, okay? That's why I do the podcasts. So the next time you're putting together a lab report, okay, just have like an earbud in and have it playing in the background. It doesn't mean you actually have to be watching it, okay? But have it playing in the background. Scroll through. Like if I'm talking about the design and you're already done that, then scroll through to where I talk about the analysis or the conclusion or whatever, so that you're reminded of what it is you're expected to do on those sections. Okay? It's not cheating. I'm putting it up there for you to use. It's a tool. Okay? You wouldn't try and take out a bolt with your bare hands. You use a tool. Okay? That's what the podcasts are. They're a tool. Okay? They're a wrench. Use them. Okay? Second question. How many people brought their labs in ahead of time to have me look them over? Okay, and how did that go for you? Okay, most people are nodding, right? Okay, now, does that mean that they brought it in and I sent them home and they never had to do a thing? Probably not, okay? When you bring your lab report in, very rarely do I say, hey, that's perfect, don't change a thing. But most of the time, I'm going to say, hey, you missed this one thing, or I think you misinterpreted this, okay? Or here's a suggestion for how to change this particular thing. So most of the people who came to me and asked for feedback got some, and it probably required them to do another 5 or 10 minutes worth of editing, okay? But that 5 or 10 minutes worth of editing probably got them between 5 and 10 marks, okay? When you think about it, a mark a minute isn't bad, okay? In terms of a little bit of extra work. Now, it's not just about the mark, though. It's also about, did I learn more because Mr. Kuder caught that error and I went back and fixed it? Okay, that's the part I'm most concerned with. Okay, your mark is your mark. That's great for you. Okay, what I'm most concerned with is, did you learn something from it? Okay, which is why I want you to come in and see me ahead of time to get that feedback. Okay, so next lab report, I'm hoping a few more people will take advantage of that. Now, when do you come and see me for that? Scheduled help or at lunch, either one, okay? I'm fine either way, okay? Because I don't have any life, okay? You just come in here at lunch and I'm in here unless it's Wednesday, second half when I'm on supervision, okay? So yeah, come in and get that help, okay? Take advantage of that. So between the podcasts and the review, okay, we should be able to do pretty well in our lab reports. That said, you guys did do pretty well, especially considering it was your first high school lab report. Okay, I was quite impressed with the quality of the lab reports. Okay, even the ones that didn't get review ahead of time and things like that. So okay, that part was pretty well done. Few little things. First thing, okay, the problem. What were you supposed to do with that? Restate it as a question in your own words. Okay, on the sheet it said something about everything's got this, and it was quite a long thing. Okay, I shortened that and restated it as, can unknown samples be identified by only their physical properties? Okay, revealed by simple tests. All right, so I just said, yeah, here's what's probably going to go on, and can I do this? All right, in the design part, the part most people forgot, which was odd because I mentioned it in the podcast, and I had right down here under controlled variables in brackets, explain your choices. A lot of people deleted that and then didn't do it. Okay, that was kind of the problem there, is people didn't explain. This is the manipulated variable because. This is the responding variable because. Okay, that's the kind of stuff that needs to happen. So your design should look something like this. Okay, the manipulated variable in this experiment was the unknown substances are the manipulated variable because the experimenter will be running the same series of tests several times, each time on a new unknown substance with unique properties. Okay, we come back to this unique properties like 10 or 11 times in this lab report because that's the whole premise of the lab, is that everything has unique physical properties. So we're going to come back to that time and time again. All right? So I identified, here's what it is, here's why. Okay? You have to have the part about the why. Okay? And the part about the why has to be more than because I'm changing it. Okay? Or because it's being changed. You have to have a little more explanation than just that. Okay? It has to be specific to this particular lab. All right, the responding variable. The responding variable is the results of each series of tests. In other words, the physical properties. Okay? They will be unique to each substance. How many times has that been said now? In every single thing so far in this lab, in the problem, in the manipulated variable, in the responding variable. Okay? They're unique to each substance, and so will respond to whatever unknown material is being tested. Okay? Now, in the controlled variables, okay, a lot of people shortcut the controlled variables, and they did it in this way. They listed all the controlled variables, and then they said, they're all controlled because they'll affect the experiment if we don't. And that's too general. Okay? If you identify 3 controlled variables, you need to tell me why you controlled each one, because each one would have a different effect on the experiment. Okay? Do you guys follow me there? Okay? Yes, I know that in general we want to control them because they'll affect the experiment, but you need to tell me how each one would do that. So, example here. The test being performed is a controlled variable. We performed the same set of tests in the same way. Okay? And we need to do that in order to be fair. Okay, temperature is a controlled variable because it can affect the results of the tests and many physical properties, in particular, solubility. Okay, so everything in there was the same temperature. I made sure of that because I left it in that room overnight. Okay, that way everything the next morning was the same temperature. Okay, the amount of each substance, because this could affect the interpretation of the results of many tests, especially the solubility test, right? If I put a whole bunch, a heaping pile in there, I'd never get it all to dissolve. Okay, distilled water is being used for the solubility tests because it eliminates the effect of minerals, which could be in tap water, okay, on the physical properties. All right, so I listed 4. You had to list 3. Okay, and I explained how each one would have an effect on the experiment if I didn't control it. You guys follow the expectations for that? Okay, for next time? Okay. All right, what 3 words does your hypothesis need to contain? If, and then. In the if part of your hypothesis, you need to talk about the premise that you're working on, the idea you're trying to prove, the answer to the problem, something like that needs to go in the if part. The premise here, all things have unique physical properties. Okay? So, if all things have unique combinations of particles influencing their physical properties, I would have been satisfied with if all things have unique physical properties. I'd have been satisfied with that. Okay? And the and part talks about your experiment, just briefly. Okay? And a series of tests to find observable properties, solubility, aqueous conductivity, and pH are performed and recorded. So all I said is I'm going to run these 4 tests. Okay? That's all I said about the experiment. I'm going to run these 4 tests. No real detail, just these 4 tests. Okay? The then part says, here's what's going to happen. Okay? You have to take a stand in a hypothesis and say, if this is true, then this will happen. Okay? Or if this is the cause, I'm going to find this. Okay? That's how a hypothesis works. So in the then part, I say, then it will be possible to identify several unknown compounds based on the results of these tests. Okay? So I've said, I'm going to do this. These are the results I'm going to get. Okay? You guys follow me there? Unfortunately, a lot of people's hypothesis went like this instead. If we run these tests, we'll be able to identify the unknowns. Okay? Which mentions nothing about the most important part of this experiment, which is that everything has unique physical properties. Okay? If your hypothesis doesn't say that, you're never going to answer the problem. Because the problem says, can you identify things based on their physical properties? If your hypothesis doesn't mention that, you're never going to know. Okay, you guys with me there? All right. Then you have your materials, okay, which was already in there for you, so you didn't really need to do much with that. Okay, in the procedure, how detailed did you need to be? Very. Remember, I said you have to assume that the person following your instructions is a complete idiot. And if you don't say every little specific thing, they'll screw it up. Okay? No offense next time you do my lab. Okay, I'm not saying that about you. Okay? But okay, your procedure needs to be very, very detailed, very specific. Okay? It needs to tell people what to do, how to do it, what to look for, and what to record. Okay? It should say all four of those things for sure. So, first thing, collect the depression plate, thermometer, stirring rod, conductivity apparatus, and pH strips from the front table. A lot of you also mentioned get your safety equipment. Okay, also good. Number 2, take equal amounts of each unknown and place them in separate depressions on the plate. Label the depressions so that unknowns are not confused. Okay, so here's where you put all of your samples. Okay, and I said take equal amounts. You guys usually said fill it 1/4 to 1/3 full, which is the same thing. Okay, everyone follow me there? We have to be specific. I had a lot of procedures that went like this. Get your goggles, get your stuff, put stuff in the plate, okay, add water to the stuff, look at the stuff, which was the wrong order, okay, so look at the stuff, add water to the stuff, test the conductivity, test the pH, and then repeat. Well, in those instructions, did you tell people how to do any of that? Because they probably don't know, okay? And if you don't tell them how to do it and what to record, they're never going to get the data they need. Okay? So, next one here, number 3, using the samples on the front table. Not the ones in the depression plate, because they're small. Using the ones on the front table, perform the observable properties test. Okay? Record the following observable properties. Color, texture, and then I explain what I mean by that. Crystalline, waxy, molten, okay? State of matter, solid, liquid, or gas. Okay? Waft the samples and record any odors and any other characteristics you feel are important. Okay? All right, number 4, using an eyedropper or wash bottle is what we used, okay, containing distilled water. Fill each depression to within 3/4 of full and stir briefly while taking the temperature of the mixture. Okay, record whether the material is soluble, and then I tell them how they'll know, based on color changes to the water, changes in the crystal shape, or any separation of the materials. Okay, here's what to look for, here's what to write down. Number 5, conductivity test is pretty straightforward. There's not much to say about that. Take the conductivity apparatus, place it in the solutions created in step 4 so that they don't waste materials, otherwise they might dump it out. Okay? Press the button and record the readings shown on the face in your chart. What am I missing in step 4? To rinse the conductivity tester between samples. Okay? Many of you mentioned that as well. Okay. For number 6, the pH test. Using either pH paper or an electronic meter, we had pH paper, okay? Record the pH of each of the solutions from step 4, okay, by placing either the strip or the meter in the solutions. Okay? Compare the color of the strips to the color code on the pH paper container, or record the number shown on the electronic meter. Okay? So I'm saying here's what to look for. Okay? Number 7, repeat these steps for all unknown compounds. Okay? Everybody with me there? Right? Detailed, explicit instructions. All right. Our data should look something like this. And so I'm going to go through the data, and as I go through the data, I'm going to go through the reasoning process that gets you to the identification. Okay? Sample A was a green crystalline solid with large trapezoidal crystals. It had a high solubility. Okay, so first off, it's a crystalline solid and it has a high solubility. Probably what? Ionic or molecular? Probably ionic. Conductivity confirms this is an ionic compound. All right, now I've got 2 important pieces of information. This is definitely ionic, and it's green. What is it? Yeah, it's the nickel-containing compound, nickel 2 chloride. Okay, that's the reasoning process. I've got enough information now compared to my list of unknowns to know what this stuff is. Okay, the pH, because it's 6, it's essentially neutral. Doesn't really tell me anything. Okay, so I got that observation, but it wasn't all that helpful. All right, for part B, B was one of the ones that was most often misidentified. And it was most often confused with something I didn't think it should have been confused with. Okay, so we're going to go over that. Okay, B is a fine white crystalline solid with no odor. Remember that I told you that day because I had already done what with it? I had already dissolved it in water. All right, because, well, I actually didn't dissolve it in water. That's the way we buy it. We can't get it in a solid form. All right, can you get salt in a solid form? So this isn't salt then, is it? Okay. Here's the other reason it's definitely not salt, which was the thing it was most often confused with. Would you put something with a pH of 1 or 0 on your food? I wouldn't, because I kind of like my insides all connected. Okay? Just saying. A lot of people identified this as salt, and that doesn't make a lot of sense to me. Okay? I'm not trying to belittle you here, but I'm saying that just there was a fault in your logic somewhere along the way there. Okay? Conductivity was also 10. All right? So we know this is ionic because it's got a white crystalline solid and a high conductivity, was highly soluble, but here's the kicker. The pH is the most important characteristic for this one. Anything with a pH of 1 is a strong acid. And all acids contain that. That was in lesson 4. Okay, and remember I said you got to refer back to lesson 4 for some helpful hints to help you identify things. All right, all acids contain this. So I go back to, to my list here of materials, and all right, this stuff doesn't have, it's ionic, but hydrogen's not listed first. So that's not it. It's not that. It's not that. It's not that. That would be the opposite because all bases contain OH. Here we go. Hydrogen chloride. This is an ionic compound because hydrogen's acting as a metal. It's listed first, which means when this hits water, it's going to split into hydrogen and chlorine. That's my acid. Okay, hydrogen chloride. Everyone follow my reasoning there? Okay, there's nothing that I just told you that's not in your notes. Okay, all right. For C, clear odorless liquid. All right, it's a liquid, so it's not what? It's not ionic. All right, so that essentially eliminates like 3/4 of the unknowns. I only have 3 liquids on here, okay? All right, the liquids I have, sorry, I only have 2 liquids, okay? I've got water, H2O liquid, and I've got ethanol, C2H5OH liquid. So it's clear, it's odorless. Let's see what else it says. Clear odorless liquid with a conductivity of 0 and a pH of 7. Sounds like water. Yeah. Okay. I would say pretty good chance anyway. All right. For D, clear liquid. Well, I just identified the other liquid, so this has got to be the other liquid, ethanol. How do I know that? Well, ethanol smells pretty strongly. Okay. It's soluble in itself. It's molecular. Okay, and just slightly basic. Okay, just slightly basic. All right. For E, red crystalline solid. All right, this is big. Red. Red's always associated with what metal? Cobalt. Okay, always associated with cobalt. So, okay, let's confirm that this is an ionic compound. It is. Conductivity of 9. So this is our cobalt chloride. Okay, for F, solid, waxy. Not crystalline. Hey, if it's not crystalline, it's not ionic. So I'm going to go back here and see if I've got any solids that aren't ionic. Okay, that's ionic, that's ionic, that's ionic, that's ionic, that's ionic. That's molecular. But last time I checked, sugar is crystalline. So it's probably not sugar. Agreed? Okay. Water's a liquid, so it's not that. Paraffin. Paraffin, I told you, is also known as candle wax. That's looking pretty likely right now. Okay? Candle wax doesn't dissolve in water. So if it doesn't dissolve, its pH is probably going to be what? The pH of the water, right? Because it can't put anything into the water if it can't dissolve. All right, so I'm just going to go down and double check here. Okay. Solid, waxy, non-crystalline, no odor, not soluble, so molecular, molecular. Yep, that's definitely candle wax. Okay. All right. For G, G was probably the toughest one. And what I said to most people was, just leave it. You can probably identify all the others, and then whatever you have left will be G. Okay? So that's what I'm going to do. I'm going to skip it because I have, I'm going to say that I have really no idea what this stuff is. I know it's ionic. Beyond that, I'm not sure. All right, so I'm going to go down to the next one. H, large, greasy, saucer-shaped crystalline solid. Crystalline solid, it's definitely ionic. It had a temperature increase and was very soluble and had a conductivity of 10. Definitely ionic, but here's the kicker. It's highly basic. Okay? All basic compounds contain OH. Everyone follow me there? Okay, that's straight out of your lesson 4 notes. Okay, so if I go back up here, I only see 2 compounds that end in OH, and one of them I already identified. It was a liquid, so it can't be this. So it's got to be this stuff. Okay? All right. For I, medium-sized, clear, white, crystalline, solid, no odor. Okay, it's crystalline, so it could be ionic. Okay? It's soluble. It could still be ionic then. All right. Is it ionic? Not with a conductivity of 2. Okay? Conductivity of 2 would indicate that this is molecular. So I need to find another molecular solid that is crystalline on my list. Okay? So I go back up to here. That's molecular. It's solid. And last time I checked, sugar is crystalline, right? Unless it's icing sugar, but generally sugar is crystalline, right? Okay, so that's what that one is. I had a lot of people also confuse sugar and salt. And the thing that should have been separating sugar and salt was this, the conductivity. Okay, for J, small white square crystals, solid, no odor, highly soluble, conductivity of 8, definitely ionic, pH around 6. I don't have a lot of things left. That sounds like table salt to me. Okay, that's sodium chloride. Okay, for K, blue. All right, we've only got 2 things left, and only one of them is blue. It would be copper sulfate. Okay, now we go back to G. There's only one thing left. Ammonium nitrate. Okay, and that's the stuff that's in cold packs. Well, that seems to fit with this. When I added water to it, it got colder. Okay, you guys follow the reasoning there? Okay. All right, so that's what you had to do in the analysis, was just fill in the chart. Okay, for your conclusion, you need to restate your hypothesis, and so basically just copy and paste it, and that's what I did, copied and pasted it. Then, to accept or reject it, I need to talk about what did I find, and what does it tell me. Okay, so my premise was if all things have unique physical properties, okay, that I would be able to identify them. So, this hypothesis is acceptable because each of the samples did have unique physical properties. There was not one thing in there that had an exact same line of observations as any other. Okay, so they had a unique combination of physical properties, and that allowed them to be classified as ionic or molecular, as acids and bases, and then identified. Okay, I said what I found in the lab, I said how it related to my hypothesis, and I could accept it. All right, simply saying I was able to identify all of them, so I was right, is not going to get you 4 out of 4. Okay, because you didn't say how you were able to identify them, and that was the big premise. You were going to identify them using their physical properties, so you have to mention that. Okay, have we mentioned unique physical properties in basically every single thing? Yes. Okay, do that whenever you have a lab. The premise of your lab needs to be mentioned all the time so people remember. Okay, sources of error. Sources of error needed to be things that you had no ability to correct. Okay, within the procedure, you had no ability to correct them. So saying things like, we didn't rinse our conductivity tester. Well, you should have. Okay, or we forgot to take the temperature of this. Well, then do it again. Okay, those are human error. If you tell me you didn't do it again. All right, that's a correctable error. So it should not be a source of error because you're going to correct it. Okay, sources of error are things that you were told to do, but you found made the lab difficult. Biggest thing, tiny samples. All right, is it difficult to do all of those tests in that tiny little depression? Absolutely. Okay, but we do that because it saves money. Okay, we don't have to have oodles and gobs of everything. Okay, so we just need little amounts. Yeah, that made the lab difficult. How do we fix that? Everyone gets bigger samples. Okay, yeah. Okay, we mention the source of error and we say, here's how it could be fixed. Right? The second source of error I listed was common source of samples for all groups could have led to accidental contamination of the samples, and that could have interfered with the collection of good data. Was there any way for you to know if the samples at the front table were contaminated? No. We did our best. We said, make sure you don't use the scupula from A and B. Okay, we said that. But here's the thing. I watched you guys, and I watch people do this every semester when they do this lab. They take the scupula out, and they hold their depression plate over the other samples and pour. Okay? And inevitably, some of the stuff falls over the edge and gets into the other samples, and they get contaminated. It happens. Okay? It doesn't usually interfere too much with the lab because we're talking like one crystal, okay, or things like that. It's not that big a deal, but it happens. Okay? Is it a source of error? Yes, it is. Is it easily correctable? Yes, it is. Okay? Next time we do that lab, or if we repeated the lab, everyone would get their own set of samples. That would take me forever. That's why we don't do it. Okay? To set that up, it would take me forever. So we just have common samples at the front of the room. Okay? Does that sort of make sense? Those are the things that we want to list. Don't ever list, I screwed up, Coderre, and I did nothing about it. Okay? Never say that. Okay? That's bad science. All right? You gotta, don't tell me that. I don't want to know. Okay? Just tell me the stuff you couldn't do anything about. Okay, for the class discussion, just quickly here, you don't really need to type these down. Okay, it's just stuff to talk about. Why do we use distilled water? Right, it's got no ions, no minerals, no nutrients, nothing in it. It can't affect any of the tests. It comes up as neutral. It comes up as zero conductivity. Okay, so it can't interfere with any of the tests. Okay. Okay, was that, you were going to answer that? Okay. Number two, what were some notable differences between the behavior of molecular and ionic compounds? Well, big ones, they all conducted electricity. All the ionic conducted, none of the molecular did. Okay. The molecular compounds tended to be less soluble, okay, and only one of them was crystalline. Okay. In terms of pH, which group of compounds, ionic or molecular, had more extreme tendencies? Well, this had a pH of 1, and this had a pH of 14. They are both what kind of compound? They're both ionic. So I would say then that ionic had the most extreme tendencies because everything else was between 6 and 8. Okay, so essentially everything else was neutral. Right. Okay, were temperature changes noted in any of your tests? Yes. Okay, the sodium hydroxide got hotter, the hydrogen chloride got hotter, and the ammonium nitrate got colder. Okay, all of them were ionic. Okay, they were all ionic. Now, that indicates that a chemical change is occurring. That's important to know. Okay, describe some changes that produce other kinds, chemical changes, sorry, that produce other kinds of energy. Well, a campfire produces heat. A glow stick, okay, when you snap them, produces light. Okay, explosions produce sound and expanding gases. Okay, things like that. Those are all forms of energy. All right, does that make sense? All right, so next time we do a lab report, we kind of know what things to focus on. Okay, hopefully you got from your lab report, where did I lose marks? What do I need to do the next time? Okay, in order to not lose those marks. Agreed? Okay. I go through each lab every time I hand it back. Okay, I don't usually go through it this thoroughly. Okay, but I'll go through each of the parts kind of quick so you can, see where you went wrong. It won't normally take as long as it took today. All right. Okay, you got the rest of the class to work on your toxin project. Yes, you may.